In Chapter 13, we'll extend our understanding of the inference about populations to the concept of analysis of variance. First, we must introduce the concept and the logic behind variance. Through the course so far, we've considered both observational and experimental data. In an experimental study, we control one or more factors so that we can determine how they influence a variable of interest. In an observational study, the factors are not controlled, and we will use experiments to look for cause and effect relationships. But the analysis of variance, also called ANOVA, can be used for both experimental and observational studies. Now for some definitions. A factor. In an experiment, a factor is the variable we want to investigate. A treatment is a level of that factor. Experimental units are the objects of interest, and ideally we'll use a randomized design in a study. In our last chapter, we considered inference about the difference between two population means. Analysis of variance, or ANOVA, can be used to test for the equality of three or more population means. Our null hypothesis will always be that all the population means are equal. And the alternative hypothesis is that not all the means are equal. If we reject the null hypothesis, we cannot conclude that all the means are different. We can only conclude that at least two population means have different values. The key assumptions that allow us to use ANOVA: for each population, the response or the dependent variable is normally distributed, and that the variances of all the populations are the same, and that the observations are independent. Looking at this normal curve, if the sample means are close enough together, the ANOVA test will help us conclude that there is only one sampling distribution. Therefore, the null hypothesis is true and all the population means are equal. When the null hypothesis is false, at least one of the sample means comes from a different sampling distribution, and therefore the means are not equal.